Hello everyone, this is Brenna, your friendly 121 LA, and this week I'm going to be talking about this leaping bush babies problem from lecture, the lecture on energy and energy transformations or conservation of energy. So this problem says this species of bush baby, and I'm not even going to try to say the scientific name, has been observed to jump to a height of 2.3 meters. Its short legs require it to lift off in a very short time, 0.15 seconds from the bottom of the crouch to when it leaves the ground. What are the key points in the motion? Describe the energy transformations that take place. How much kinetic energy does it have when it leaves the ground? And compute the power and the power per kilogram for the bush baby. Alright, so first we're going to start off with describing the key points in the motion. So I know that the bush baby is jumping, right? It says that it's in a crouch, and sorry about my bush baby. And then usually we focus on when it's about to leave the ground and then when at the highest point in its motion. So we have crouch, we have ready to leave the ground, and the highest point. And I'm just going to write what I know so far. So in the crouch, we know our speed is equal to 0. We're not moving yet. When we're getting ready to take off, we know we have a velocity of something. We're not quite sure yet. And at the highest point, we know we have an acceleration of 9.8 meters per second squared because we are in free fall. And let's see, what else do we know? I can do a couple of things with distances here. I know that this distance, which is probably y, since we're talking about energy, is 2.3 meters. And this distance here is, what does it say? It does not say, but we know that the time for that is equal to 0.15 seconds. Okay, so we know that much. Next, we're asked to describe the energy transformations that take place. Okay, I'm going to do energy transformations in blue. So if I look at the crouch, usually when we're thinking about jumping, we're springing up, right? We store some elastic potential in our tendons or our ligaments or muscles or whatever. So I'm going to say we have spring potential right there. We're getting ready to leave. Well, we're moving up, and since we're moving up at some speed, I know that we probably have kinetic energy there. So I'm just going to label this K initial. And then the final piece, when our velocity is 0 at that highest point, I know that we have gravitational potential. Okay? Because we're some height off the ground, getting ready to fall back down. We have the potential to fall back down. So here's our energy transformations that take place in each step. The next question asks, how much kinetic energy does it have when it leaves the ground? Okay, well, if I really look at these steps, I know that the amount of spring potential has to equal the amount of kinetic energy, which has to equal the amount of gravitational potential. And if I write the equations for that out, I have 1/2 kx squared is equal to 1/2 mv squared is equal to mgh. Now I have to find how much kinetic energy does it have when it leaves the ground. Well, if I look at these, I don't have really anything about this piece. So I'm not going to use the spring potential energy. I know it's there, but I don't have to use it. What I really know stuff about is the kinetic and the potential, right? Because I have a height, and sorry, I wrote h instead of y, so let me erase that to put a y there. I have y, I know it's 2.3 meters. I have g, and I have the mass, and so I can solve for kinetic energy. So if I go ahead and solve for kinetic energy, I know that mgy is equal to the amount of kinetic energy. I could solve for speed, but I don't think I have to, since both of these are equal. all I'm going to have to do is solve for the gravitational potential energy. It's equal to the kinetic. Thus, we find out how much kinetic energy the Bushbaby has when it leaves the ground. So if I calculate this, the mass is 0.3 kilograms. Gravity is 9.8 meters per second squared. And y is equal to 2.3 meters. And if I calculate that all out, then I get 6.76 joules for kinetic energy. And to me that seems pretty reasonable because, this animal isn't that big. It's pretty small. And I'm not going to expect a huge amount of energy. But that's still big enough to get it off the ground. Okay, so we found the kinetic energy it takes for it to leave the ground. Now we're asked to compute the power and the power per kilogram for the Bushbaby. Well, power is equal to the change in energy over the change in time. Okay, well, since I know that the spring potential energy is equal to the kinetic energy is equal to the gravitational potential energy, the change in energy stays the same the entire time. So I know that I can use 6.76 joules for that change in energy. But what do I use for the time? Well, the spring potential energy is also equal to 6.76 joules, so I can just use the time of that crouch piece, that liftoff piece, to give us our power, right? Because it's all the same. So 1.15 seconds, I get a power of 45.1 watts. And that's pretty good. That's a pretty big power, which, if you know Brian, the Bushbaby is one of his favorite animals to do analysis on, and they're quite remarkable. So I'm going to say this makes sense. Based on what I know, just a little bit about Bushbabies, they're pretty remarkable, right? Next, we're asked to find the power per kilogram. We call power per kilogram, so power per kilogram, we call that specific power. And specific power is found just by taking the power divided by the mass. And so if we go ahead and do that, our power is 45.1 watts divided by 0.30 kilograms. Our specific power is, and actually I did not do this calculation before I started, 45.1 divided by 0.3, it's about 150.33 times the mass. That's how big our specific power is. So our energy, or our power, is 150 times the mass, which is really incredible. And you can also write this as 150.33 watts per kilogram, if you would like. So for every kilogram of mass, this Bushbaby is exerting 150 watts of power, which is pretty impressive. And I think that is all for that one. So I will see you in the next one.